Right. Yeah, yeah. Yeah, the basement is like covered in this kind of wall too. So if you ever want to go study down there, works pretty nice.
There's over here too.
Yeah, if you guys want to come migrate over to the other side.
Yeah, you could bring in the chairs outside or something.
Yeah, yeah. If you guys want, you could grab the ones from outside as well. Yeah.
Hold on, the angles. We're still going about the triangles of those.
I have to go to the lab.
Oh.
Yeah. To go to, and then maybe to get an account, but I have to do a lot of that basically. So.
So basically, the status of the midterm, just to give you like a little bit more detail on how the things go work. Has he given you like a brief explanation of the structure of it? Did it make sense to you guys?
Five questions, like 6 points per question.
Yeah, exactly. So, yeah, I've had a few people like mention it doesn't make a ton of sense. So there's have you ever taken like a quiz on Canvas before?
Yeah.
Yeah.
Okay, yeah. So there's 5 separate quizzes. I'll write bigger. But yeah, there's 5 quizzes. Each quiz has 5 problems to it. And then each problem shouldn't take you that long because there's 25 of them. It's like an hour and 15 minutes of an exam. You get 2 attempts. For each problem. Out of your 2 attempts, I believe they're averaged together. So if you get like, for one of the quizzes, you get, let's say 2.5, and then the second time you get all 5, you'll get like, what is that, like 3.75 out of 5 for the whole first quiz. And then I don't know if he's still doing this, but in the past he would drop one of the quizzes. And then yeah, that's kind of like the structure of it. Yeah, thank you. Any questions on that before we start just like solving problems?
Is it in like a computer lab?
No, so it'll be in your regular classroom. And he's gonna try and like space people out evenly, like one person like every other chair or whatever. You're gonna have your laptop out, open book, open notes. You can use your calculator. No ChatGPT, no Google. I think that's pretty much it though. But if you have like a PDF version of the book, you can just like scroll through the book, control F the book, kind of whatever, you know. Slides are fair game. The more material you have, the like more confusing it's going to be, like trying to sift through all of the material. So it might make sense to make like note sheet with like a bunch of handy equations so that you can pump through a lot of the questions quickly. Yeah. Okay, so let me swipe through here. So yeah, op amps, chapter 3, diodes. Okay, so 5 quizzes. 2 of those quizzes are going to be for diodes. Two quizzes are for your op amps. And then one quiz is going to be chapter 3. So I made a bunch of, originally there was going to be no chapter 3 on the midterm. There's historically never been any chapter 3 on the midterm, which is why I told you guys there's going to be no chapter 3 on the midterm. He sent me an email after I did the lecture, like a week after I did the lecture, and he was like, you should make questions for chapter 3 instead of having some more op-amp questions. So now you have chapter 3. I made a bunch of questions. He said they were too easy like an hour ago. So I'm going to give you more questions. There's probably going to be 10 chapter 3 questions worth half a point each. So be aware, 5 are from the slides. The other 5 are going to be numerical questions directly from your homework. I'm going to basically copy the exact structure that you had for the homework for those. The ones you actually did, not the ones that he suggests you do. So yeah, just
So we won't have to find like depletion.
dude, I haven't even looked at chapter 3 questions yet. I'm gonna learn that today, and then I'm gonna write those probably tomorrow. But yeah, so based off of this distribution, most of it's just diodes and op amps, right? So if you're gonna study anything, if you're time crunched, diodes and op amps are gonna be where you should spend most of your time. And then you can immediately get half your points, apparently, with these 2 easy questions from chapter 3 from the slides. And then if you have time, you can study the homework from chapter 3. Yeah. Okay, that was even more detail about the structure. Any other questions?
Do we have to like turn in paper of our work or anything, or is it literally just on Canvas, put your answer in and that's it?
Yeah, it's multiple choice. You just put your answer in on Canvas. I don't think it tells you. So like if you get a question wrong, right? I don't think it'll tell you like what you answered and say that it's wrong. I think it'll just say you got like 3 out of 5. So it would kind of make sense to write down what you answered for each question if you have time. Oh, and there's a sign-in sheet. I'm pretty sure he's gonna like sit everybody down. He's gonna start the quiz, and then he's gonna go walk through the aisles of everybody and like have everyone sign in with the sign-in sheet. Bring your red ID or a driver's license or a military ID. Any of those 3 are like totally adequate. In the past, I accepted pictures of IDs because he wasn't there. I don't think he lets that fly if he's there and he's gonna be there. So, yeah, just keep that in mind. Okay. Yep. Any more questions?
So the 2 attempts are during like the actual class session, right?
Yeah.
Like if you only have time for one, then the second it doesn't matter.
Yeah.
Okay.
Yeah. Yeah. And if you get like a 4.5 out of 5, then
Yeah,
like, move on to the next question.
Would you recommend doing like both attempts to one question and then moving on to the next one, or doing like one attempt for all of them?
I feel like it matters more on how you learn and how you like process information and less like a general rule of thumb. Because like for me, I would do it and then I would skip on, like move on to the next stuff, and then I would come back just because like my brain will dwell on it while I'm doing other work. But if that doesn't really work for you, then maybe do both at the same time. Yeah. Cool.
Will the second attempt be different questions than the first?
No, same questions. I think they're even in the same order. And they definitely have the same like options. Yeah. I don't know if the options will be in the same order though. You know, they might shuffle the A, B, C, D or whatever.
Okay.
Is he curved?
Not really. I think he did it for 430, but I don't think he ever has for 330. Yeah. Most people do pretty well on this class. Not everybody, but like. Okay. Any other questions?
So each topic's gonna be one of the different quizzes, or is like one of the problems are gonna be? How many problems each quiz? I'm confused.
Yeah. So each quiz has 5 problems.
Okay.
Yeah.
So there's 25 total,
Yes.
except for chapter 3.
Except for chapter 3, which has 10, so there's 30. Unless I can talk him out of adding more.
Wait, why is it 10?
Because of the lack of communication between him and I.
So you get the short end of the stick.
Yeah, that's what I'm saying. I sent him an email like 10 minutes ago, so we'll see.
What
Yeah.
if we send him a video of all of us just like?
I don't think he'll care. I'm kidding. He's a nice guy. I'm just messing with you. Okay. Any other questions?
So like for a quiz, will it be like one circuit and we answer 5 questions about that circuit, or will it be like 5?
Yeah, that's a great question. I think midterm 2 and the final is more similar to what you're describing. Midterm 1, I think they're all discrete. So they're all just different questions. So like let's say one of the first quizzes has op-amps, right? It'll be like 2 really simple op-amp problems, and then it'll be like another op-amp problem where you'll have to think a little bit, maybe do like some hand calculations, and then it'll be like a really difficult op-amp problem. It's kind of like that. And then there's 2 of those, so same structure for both of the quizzes for op-amps.
Oh, for the midterm and final, is that the same structure as the first midterm? Like, would it be multiple choice?
Yeah, it'll be exactly the same general structure. Show up on your laptop, multiple choice, 5 quizzes, 5 problems each. Just more difficult for the final.
Or
Yeah.
is cumulative or so?
No, the final.
No. Okay, probably.
It's like it's like this one's what, 3 or 2 through 4, and then I think it's 5 and 6 and 7.
Okay.
Yeah, that's how it is.
For the diodes and op-amp section, are those questions coming from the homework or from the slides, or where are they coming from? Is he just making them up?
So when you buy a textbook and you're a professor, they give you like a massive stash of questions to like give to people for like tests. But most of those questions have ended up online. So a lot of professors make their own. I think his are like slightly modified versions of those. Yeah. Cool. You'll see a lot of them are like slightly photoshopped. Yeah. And then any of the ones that I wrote have spelling mistakes, so you'll be able to spot them.
Real.
Okay. Any other questions before we start? Okay, cool. I'll start with like an easier op-amp circuit. This is like mid-tier as to what you would see on the midterm. Does anyone care if I erase part of this, like the right-hand side? Cool. Okay. V1 is gonna be 1 volt. And then V2 is gonna be 3 volts. Relative to ground. Can everyone see this all right? Like, is it showing up? Contrast is all right? Okay, sweet. So, the first thing you need to know about op amps is that you're gonna have no current going through the positive leg and no current going through the negative leg. but you have the same voltage here as you do here. So the very first thing that I'm gonna do is I'm gonna like label these things. So if we got V1 and V2 already, then I'm gonna say this is V3. I'm gonna come up here, I'm gonna label this, I'm gonna say it's V4, right? And then the very first step after that would be to figure out like the easiest current path. So we know this is ground, we know the potential here, and we know that this is just a really simple like 50-50 voltage divider, right? We know we have 3 volts over here. So I could go and write out like the voltage divider rule, but since it's 10K and 10K and 3 volts, I'm just gonna say this is V3 equals 1.5 volts. Is everyone following me so far?
That was just like a mental calculation.
Yep. Yeah, I could write it out though. So we could say, I always do this the really long, slow way, which is why I'm avoiding it. But typically what I would do here is I would find the current. So I'll call it I1. And then I would say I1 equals, so V equals IR. That's just Ohm's law. And then I would say I1 equals V divided by R. And then I would define what V and R are. So V in this case would be V2 because the current flows from the source of highest potential to the source of lowest potential. And then R would be both of the 10 kilo ohm resistors in series because there's no current flowing into the op amp. So this would just be 20K. So I'll just say it's R, and then I'll write another line here. I1 equals 3 volts divided by 20 kilo ohms. So grab my calculator. 3 divided by 20,000 is 15 microamps. I1 equals 15, sorry, 150 microamps. 150 times 10 to the power of -6. Right?
And V3 is just the voltage drop from V2 to that node, right? Across the first resistor.
Yeah, to ground.
Oh, to ground.
Yeah. Are you guys used to seeing ground as like that?
Yeah.
Okay, sorry about that. Yeah, so that's also it's another symbol for ground. It means the same thing. It's just a triangle. It's quicker to write, so people write it that way. Yep. So now that we have I, we want to figure out the voltage here. So we could either say 3 minus V3, and then use the I and the R, or we can just say that the voltage drop across this 10 kilo ohm resistor is what's going to be sitting at V3. So I'm going to go ahead and define V3 over here. So V3 equals 10 kilo ohms times 150 times 10 to the power of -6. So 10 kilo ohms times 150 times 10 to the power of -6, that's 10 kilo ohms times 150 microamps. Again, just deriving it from Ohm's law. So V3 then equals 1.5 volts. If you if you multiply it over. And then now that you have V3, can anyone tell me what V4 is?
1.5.
Yeah, okay, perfect. 1.5. So yeah, if you were able to do that mental math, then you would save yourself like quite a bit of writing effort. So practicing just like looking at a circuit and then pumping out those equations really quick can save you a lot of time, get you a better grade. So if we have 1.5 here and we have 1 volt here, then we can solve for I2, right? And then once we have I2, then we can have I3. because there's no current going into the negative pole there. So another way of saying this is just I2 continues on. So if I'm gonna go ahead and solve for I2, then I would say we have 1.5 over here, we have 1 volt over here, we have 10 kilo ohms. Again, it's just Ohm's law. So V equals IR. So in this case, V is V1 minus V4. Yeah, I'll redefine the current because the voltage at V4 is more than that at V1. The current's going to flow this way. So I'm just going to define it that way so I don't have to do any mental tricks. Yep. Equals I, which is what we're looking for, I2. And then times R, which is 10 kilo ohms. So to make that all numerical, 0.5 volts divided by 10 kilo ohms equals I2. So that is 50 microamps. All right. And now that we know I2, then we can go ahead and solve for VO. We know the current's flowing this way, so we know the potential here is going to be higher than the potential here. And we know that we're getting half a volt of voltage drop over here. So in theory, you don't even need to do those calculations. You could just say that VO is half a volt over V4. Or if we want to do the calculations, we can say VO equals 50 microamps times 10 kilo ohms plus V4. So VO equals, well, we know this is half a volt, so 0.5 volts plus 1.5 volts. VO equals 2 volts. Or if you want to do this like the really, really simple way, then you would say no current here, no current here. You have half the voltage dropped here, so you end up with 1.5 volts. You have 1.5 volts here, you have 1 volt here, so that means you drop half a volt here. And because you're dropping half a volt here, then you're also going to drop half a volt here because you have the same current and the same resistance. So therefore, you add that half a volt to your 1.5 and you end up with 2. So in theory, like if you looked at this and you were really confident in yourself, you could do it very quickly. I don't think there are any symmetrical problems like this on the final, or sorry, on the midterm, but there's one that's really similar to this in structure. So being able to do it longhand makes sense. Cool.
We started with V2. We found V3 first just because V2 is connected to ground. Is that why we found V3 first?
Yeah, because this is the simplest current path to calculate.
Yeah. Okay. As opposed to the top where it's like going to V0.
Yeah. You don't know V0, you're calculating for it, and you don't necessarily know what the voltage is here. So this current path becomes like ambiguous.
Right.
Yeah, there's one, what is it, like one equation but two unknowns kind of thing. Yeah. Cool. Any other questions on this one? Nope. Okay. Cool. Does anyone need to write more before I erase it? Okay. Sweet. Okay, so that was originally going to be the second one I did, but I figured I'd warm you up to this one. This one is, I would say, on the upper scale of difficulty for these problems. But there's one on the final, or sorry, on the midterm that's more difficult than this one. So let me write it.
And you said it's multiple choice?
Mhm.
So like that op amp would have been multiple choice.
Yeah, so they would say like 2 volts or 1.5 volts.
Oh, okay.
Okay. I think that's it. Oh. Yeah. So initial reactions, what would be the first thing you do?
That bottom op amp has 0 volts across its 2 terminals.
Yep, exactly. So 0 volts here, 0 volts here. Now what?
Is that because it's connected to the ground on the plus part?
Yeah, yeah, because there's no current flowing here, you have no voltage loss across your 10 kilo ohm resistor and therefore 0 volts. Okay, next step.
How much is there V? Or is it arbitrary?
Oh, right, my bad. 1 volt. Makes math easy.
All the current from the 1 volt is going through the bottom part, like, I don't know if that made sense, not to the top because there's no current, so then all of the voltage drop from V and V0 is on that 10K.
Yep. So I'm just gonna label this current that you just mentioned. Let me see if I have another color here that works. Oh, I do. Fantastic. Actually, there we go. I'm gonna label it I1. Yeah, so what you just described is I1. So we can say that let's put calculations over here. I1 equals V in divided by 10 kilo ohms. So just whatever 1 divided by 10 kilo ohms is. I'll just leave it like that because it's easy. And then from there, next step.
Because there's no current in that 10K resistor, does that mean the voltage drop or voltage at the plus side is also VN?
Yep. All right, and then what can you say because of that?
The same as the negative.
Yep. Exactly.
For I1,
Mhm.
why is the 10 kilo ohm not in series with the 20 kilo ohm series? Since there's no current going into the negative terminal.
They are.
Oh, so then when we found the current up there, is it not VN over 30?
It
Or
isn't
why not?
because you have 0 volts here. So we're just
Oh, it's
finding.
just, okay, I see.
Yeah. So we're finding the current through this 10 kilo ohm resistor, and then we can extrapolate it and say there's only one way for it to go.
Okay. Thank you.
Yeah.
Could you do that though? Like, could you combine them in series or not?
Well, we don't know what this point is yet. So no. Yeah, it's not enough information.
Could you use Ohm's law to solve for that bottom half up there, now that we know I1?
This one?
No, the negative part of V naught. Like that bottom node coming out of the, yeah.
Oh, yes. Yeah, we'll do that next. So, I'll just call this VO minus. So VO minus would then be your voltage drop from here to here. And you'll note that this is 0 already, so we're gonna end up with a negative voltage on the other end. I could do this longhand, but for the sake of kind of trying to get you guys used to doing these quickly, I could say that I have 1 volt here, current is conserved, and we drop 1 volt across 10 kilo ohms. So we're gonna drop 2 volts across 20 kilo ohms with the same amount of current. So this is negative 2 volts. Does that make sense? You're saying no.
Sorry.
With your eyes. Okay, I'll just write it out longhand. So VO equals I1 times 20 kilo ohms. I1 is 1 over 10 kilo ohms. So 1 divided by 10,000 is 100 microamps. And then I can multiply that same 100 microamps by 20 kilo ohms is 2 volts. Does that make sense? Yeah. Sweet. Okay. Next step.
At the top, because now we have the voltage drop across the 10K, you know, the current going that way is,
Yep.
yeah, the 1 minus 0 the 10K.
Exactly. Call it I2. My bad. Thank you. So I2 would be exactly the same as I1, just because it's 10 kilo ohms, you have 1 volt, right? Same thing here, 10 kilo ohms, 1 volt. I2 equals 1 volt divided by 10K equals 100 microamps. All right. Next step.
With the same logic that we used on the bottom one, since we know that, because we got the same current for I1 and I2, could we also say that it was just resisting 1 volt? So then we know that V plus is ground, basically. Or not ground, but 0 volts. Because it's 1 volt there, then it'll resist that volt.
So you're on the right track, but I1 goes like this, right?
Yeah. Oh, so it'll be +1?
+1.
Oh.
Yep. Yeah, just gotta keep track of where you have a volt, which direction your current is flowing, because you always have more positive on the back end of the arrow, so to speak. So your VO positive would then equal 2 volts. I can write that out. Does anyone want me to write that out? Okay. I'll take that as a, you understand what's going on. So what is VO? Yep. Yep. So VO equals VO positive minus VO negative. Or you could say like, yeah, that's the easiest way of describing it. VO equals 2 minus negative 2, which equals 4 volts.
So is that how you handle finding VO when it's not connected to ground? It's just the difference between its two terminals?
Yep.
Okay.
Yeah. Yeah. So this would be what's called a differential output amplifier. Yeah, it would be, so it could be as you have a grounded input and like a single voltage input, and then you end up with basically 2 decoupled outputs that you reference in relation to each other.
This is a superposition problem.
I'm not super familiar with the definition of superposition.
Taking 2 components and add them together.
Yeah, from that definition.
That's in the book, I think that's what we're trying to do.
Oh, okay. Yeah, yeah. This is. I think this might have been in your homework, maybe.
Yeah.
Yeah.
Could you like, oh, sorry.
I was just saying, could you confirm one more time how the top op amp, the positive, like how that's 1 volt?
Yep. Yeah. So you have no current passing into this negative leg here. So you have no voltage drop across the 10 kilo ohm resistor, which means you have 1 volt here. And then because op amps are op amps, you just say whatever voltage is here is also at this other leg. Yeah.
Why was VO minus negative 2 volts again, and not 2?
It's negative because you have 0 volts here, and then looking at the butt end of the arrow, that's your more positive side. Therefore, everything over here has to be negative.
If you do KCL, so it'll be 0 minus VO over the 20K. So then it's just 0 minus VO. So that's negative. That makes sense.
Yeah.
So if you do the KCL here, that's what's negative.
Did you like hint at what that harder one could be? Is it like multi-stage or is it?
Yeah, so just like this way, that's the way we made the curve.
Okay.
So,
I'll get to that. That's different. I wouldn't say that's harder, that's just different. Yeah, so this is it is also a differential amplifier.
Okay.
Yeah, that's
So you can like still take it apart like one by.
yeah, pretty much all op amp problems. You can use V equals IR and then just understand that the voltages are the same at either leg and there's no current going into either leg.
So if you're stuck, go for that.
Yeah.
Okay.
Yeah, this is definitely like the slower way of doing it, but it gets you what you want 100% of the time, and you only have to use Ohm's law to get it, which is why I like doing it this way. Cool. All right. Anyone mind if I erase this stuff over here? Yeah, so we didn't really have enough time to go over this stuff today, so I'm just gonna give you like a really brief explanation of one of the op amp quizzes. So you're gonna need to know what a differentiator and integrator look like. and you're gonna need to know their transfer functions. Did they cover this in the homework? The differentiator and the integrator?
Yeah.
Okay, cool. So nothing's particularly crazy about these problems. Just know what they look like and what their transfer functions are, and then read the problem slowly and you'll be fine. This is chapter 2.5 in the book. This book is actually like pretty good. Yeah. So you have integrators, you have differentiators. What's the other key like capacitor led op amp circuit in the book? Can anyone tell me? Or like what he taught? I don't know if he taught it, but if he taught it. No. Okay. There's another one. It's called it's really similar to a integrator. I didn't write a picture down. Fucking no. Okay. You're gonna have a resistor here. You're gonna have a capacitor here. You're gonna have your op amp. I don't know if it's plus minus or minus plus, but the key thing is that a Miller integrator is gonna have a resistor and a capacitor, and then another resistor here, I think. This is really the key part of it, though, and you should know those well. I don't know them well enough to like give you a solid lecture on them, so I'm not gonna try. But you should study like whatever you can find in your homework on those.
Anything that looks like that, or the specifically the differentiator integrator?
So for these two, just like know their equations and like kind of understand what they look like. For this one, just like actually understand it.
Okay.
Yeah.
And did that have a specific name?
Miller integrator.
Thank you.
Yeah. Should write that down.
Will it differentiate like the diagram a lot from that? Or like will it deviate from that?
I can't tell you that.
Fair enough.
Yeah. Yeah.
Are we gonna have to deal with input resistance at all?
You mean like sorry, what was it?
Like just like finding.
You mean like dealing with like non-ideal op amps where there's like a small amount of input? No. Yeah, that'd be brutal. That would suck. Yeah, I think you guys understand op amps well enough. I was gonna do another one, but I think it'll be fine. Yeah, so moving on to chapter 3. Does anyone care if I erase the op amp circuit? Cool. Okay, really random quick question. Does anyone care if I like take a picture of you guys? Because he doesn't believe people come to my office after. Like honestly, do you care?
Yeah.
Okay, cool.
He said no one came to his office. Or not yesterday, the day before, but.
Yeah, he wanted me to he wanted me to join the Zoom call for like our lab right now. And I was just like, he was like, if anyone shows up, then you don't have to. I was like, okay. But this is just proof so I can get out of going to my meetings. He scheduled it after I made the office hours for what it's worth. Anyways,
It's okay.
I think it's just yeah, there's like 20 of you guys. It's totally worth my time. I'm not saying that in like a ingenuine way. I like actually mean that. Um, okay, so yeah, I'm not great at drawing, so I'm just gonna try to draw those diagrams that I showed you guys in class the other day. Um, really quickly. So circle, circle, circle. I was gonna do this on my iPad, but I don't think it's as fun. Okay, sweet. So, can anyone tell me what kind of semiconductor this is? Yeah. Well, yes.
Like, it doesn't have like, any holes in there. I don't remember.
Yeah, no, you're 100% correct. It's pure silicon. So technically still a semiconductor, but it's not N-type, it's not P-type. It's just boring silicon. I'm not gonna go through the whole lecture. I keep telling myself this. But can anyone tell me how to get P-type like a semiconductor out of this?
Phosphorus.
Yeah, I think it is phosphorus. But what's special about phosphorus?
It's like 3 valence.
Yep. Yeah. To get P-type, you need one that has 3 valence electrons. Why do you need 3?
So that there's a hole.
Yes. I didn't draw the electrons, but there would normally be like electrons in all of these spots. And then you erase one, now you have a hole, and it stole that electron. So now that we have P-type semiconductor, what's special about P-type semiconductor? It's positive. P-type. Positive type. Yep. That's all I wanted to say about that.
Is that like a question? Like.
Yeah. I mean, not exactly. It's more complicated than that, but like if you understand like why you need something to dope, if you understand how it affects the lattice, and you understand the name, and you understand what the name means, then like you can figure it out. Yeah.
So like the atom in the middle is it steals the electron because it's more electronegative.
It's 1 electron negative. Is that what you said?
I said it's more electronegative than the silicon.
Yeah, I think technically like just like how the thermal effect makes like some electrons pop out of these valence bonds at some point in time and then just go into the lattice arbitrarily. This electron would sometimes be here, and I think it would also sometimes be here, and you would have a hole. But it's like easier to just say that this one always has it.
So it's missing an electron, that's what makes it positive.
Yes.
Okay,
Yeah.
and then the blue circle is an electron.
Blue circle is a hole.
Oh, it's the whole, okay, gotcha.
Can you talk a little about you releasing the solutions for homeworks 3 and 4 before your term to study?
One of those do.
Sunday.
Wednesday.
Okay.
He normally does that. Yeah, so I'll talk to him.
There's 2 assignments due. There's one Sunday, one Wednesday.
Yeah, I'll make sure we'll make sure we post those both on Sunday. I'll make sure that's okay with him to do that, but I don't think he'll have any problem with it. He'll normally make me post on like the Monday before a test that's on Thursday. Okay, this one's a lot harder to draw with my skills, so bear with me. I might also skip the last one. Okay, so you have a bar of silicon, right? You're gonna have a P side, and you're gonna have an N side, and up here, you're gonna have a couple of terminals. What can you say about this PN junction? Diode. Yes. But since the diode is currently disconnected from everything, there's no charge. It's not reverse biased, it's not forward biased. It's just sitting there. It's open circuit. Also called equilibrium. And if you look at the like charge throughout the device, I don't know if you guys remember that video that I showed, but it's basically the depletion region kind of looks like this. In the picture, it actually lines up with the depletion region. So if you were to like draw a couple of lines down, you'd have this like gradient within there. But what can you say about VO? Like, how would you define VO?
0.7 volts.
No. You're close though. You're really close. Yeah, I did not write down the exact word I'm looking for. Oh, right. Barrier voltage. That's your current barrier voltage. Okay. What can you say about this PN junction?
Reverse bias.
Yeah, reverse biased. So it's reverse biased. What happens when you reverse, well, sorry, what happens to the barrier voltage when you reverse bias a diode or a PN junction? Bigger, yeah. Yeah, exactly. So you have a VO plus VN now for your barrier voltage. Yeah, that's pretty significant because that barrier voltage expansion is what makes reverse biasing prevent the current from flowing the opposite direction through a diode. If it didn't expand, then it wouldn't do what we all consider to be a typical diode functionality. Cool. Okay, so what's that one?
Forward biased.
Yeah, there you go. Forward biased. And then now what's special about that? Barrier voltage.
Barrier voltage is smaller.
Yeah. And going back to what you were saying, this is where you're getting that like 0.7 from. Yeah. It's after it shrinks, it becomes that like 0.7. Yeah, I don't actually know what VO is like intrinsically. I'm sure it's in the book. I didn't read it.
So this also has something to do with the breakdown voltage, where if you exceed the barrier in the opposite way, it'll stop functioning as a diode?
Yeah,
Okay.
yeah, yeah. It's a good connection. I don't know if you read my slide here, but you're stealing my material.
What is the like what? That's my question. Like, what is the barrier voltage? Like, what does that signify? That makes sense. I don't know.
Yeah, no, it makes sense. The barrier voltage is like it's equal to and a little bit above whatever voltage you're applying to your diode.
Okay.
Sorry, wrong quick. This one. It's equal to and a little bit above the voltage that you're trying to reverse bias with. Can you restate your question one more time?
I was just curious, like, what the barrier voltage is.
Yeah.
Like, what significance that has.
I think it's literally like let me draw a little circuit here. So let's say you have a voltage source, plus, minus, and you have a resistor here. Let's say it's like 10 kilo ohms or 10 ohms, whatever. And now you have another voltage source here, plus, minus. And let's say this is 10 volts, right? And let's say that this one is also 10 volts, but it's not just 10 volts, it's like 10.0001 volts. Like, you're not going to have current flowing this direction because this one is just like ever so slightly above it, right? This is kind of like what the internal chemistry of the diode is doing in real time as you were to like adjust this. It's adjusting its internal voltage to be just above whatever voltage you're trying to push through it.
Okay.
Yeah, or at least that's how I think about it. Yeah, I didn't take that from the book, but that's the implication. But then you don't have any energy stored inside the diode, so it doesn't push current back the other direction.
It just prevents it from flowing through the diode?
Yeah.
Okay.
Okay. Can anyone label these regions of a diode?
Oh, I just had a question. So is the reason why the middle one reverse bias is because the positive end is like connected to the negative end of the source, and then the reason why the other one's forward bias is because positive and whatnot.
Yep. Yeah. Just making sure I didn't write it backwards. Okay, yeah, so regions. Let's call it, let's just say there's two. There's this one and there's this one. What's that one? Shit, let me label the axis. Current, voltage. Yeah, so what's the right hand one?
So that's the forward.
Yep, yeah, forward bias. Okay, and what's the left hand one? Yeah. Okay, and then what happens if we keep going this direction? Yep. Yeah, okay, you guys got it. We'll erase the top part. Is everyone done? Everyone done with the top part?
Could you explain a little more about what the breakdown voltage is? Or what it's used for?
Are you a physicist or are you an engineer?
I'm just curious.
Or I mean, like in this context, like in this theoretical question, are you asking me as a physicist or are you asking me as an engineer?
Engineer.
You don't worry about it.
Okay.
Yeah.
Could you say that it's because the source is filling all the holes of your diode and then it'll stop functioning?
So when you reverse bias a diode, it physically I'm pretty sure it physically expands your breakdown region. And that expansion, actually, it's not physical. I think it's electron. Dude, I'm so sorry. I'm not a physicist. But the really, really bad way I think about it is like there's a certain amount of charge that's created, and that charge expands the like magnetic field or electric field, I don't know which, inside of the diode, which when that expansion occurs, then it prevents current from flowing.
Hmm.
Yeah. If you want, watch that Veritasium video, like that 3 minute segment, it will explain it way better than I can. That is also kind of an engineer's guide to the same like mental problem. Not a physicist guide. Yeah. I know you guys are fresh off of physics. It's been like 7 years since I've taken physics, so I'm tripping. Yeah, if you do end up working with semiconductors, like if you go work for like Qualcomm or ASML or somebody who works like really low level, you might actually end up caring. But at like a high level, like a discrete component, I'm kind of teaching this like I'm assuming you're gonna go and do your senior design project and you're gonna be like, which diode do I want? From that perspective, it doesn't matter as much. Okay. Oh yeah, so chapter 3, still really undecided as to what's gonna happen with those like numerical questions. I looked over the ones you guys did with your homework. There's 5 of them. I can't tell you which one I like the most or which ones I like the most. They all looked fine, like one equation problems. Yeah, so TLDR, sorry, but it'll be from your homework.
Wait, if it's 10 and 5 are coming from the homework and there's only 5, then it's not one of them.
The other 5 are from the slides. So like what I taught you just now, and then what I taught you guys like last Tuesday.
You said we could use the slides, right?
Yeah. You can pull up the slides and like go through them, like while you're taking your test.
Can we use our iPads as like a second monitor?
Yeah, a lot of people take notes on their iPads and then like have the test open on their laptops. Yeah, sometimes people will have like their calculator, their iPad, their computer, and like an energy drink.
Yeah.
Make it through.
Crazy to put that all on the tiny little.
Dude, people make it fit. I swear to God, when I was teaching 430, they had these like desks for the final instead of like the little desks. And this one lady had 4 energy drinks stacked all on top of each other. She didn't go through them all, but she had them there.
The mental like,
Yeah. It's like emotional support musters.
Were they all the same color or they?
No, she had a variety. Yeah.
It's 800 milligrams.
Okay. Everyone done with this one too? Okay, cool. Diodes. Everyone loves diodes. But like actual diodes this time, not like physics stuff that I'm unqualified to teach. we, um. Do you guys remember how I taught you like that really briefly? I taught how to do the like time analysis of these kind of circuits. Okay. I did it kind of shittily. So if I'm gonna draw like one common y-axis, and that's gonna be voltage. And then on the top, I'm gonna draw my sinusoid. I'm just gonna go ahead and like label the vertical axes, where it like crosses, like the 0 points again. And then on the bottom, I'm gonna have my VO. So this would be V sign. So for this first negative half wave, right? We're gonna have positive voltage at ground, and we're gonna have negative voltage at the top rail, right? What during this period, what would VO be? I don't judge any guesses. You're guessing 0. Yeah, you're right. 0 volts, right? Because if you have positive here, actually, let me do that in blue. If you have positive here and you have negative here, right? What is I1? 0. And if you're measuring VO across this R, you're not going to have any voltage drop across it because I1 equals 0. Okay, so that's this first section here. What does this section look like?
Is it the sine wave?
Yeah. Yeah, you're gonna go from 0. Oh shit. This is my 0 point. It's gonna be 0, and now you're gonna have your sine. Okay, and then this section. Next one. 0 again. Yeah. There you go. Does that make sense?
Why is I1 0?
For this period,
Yes.
I1 is 0 because you're reverse biasing your diode.
Oh, it can't flow through, okay.
Yeah. Okay. So added a capacitor. And now I want you to draw for me, instead of this first section, let's draw this second section right here. What would this second section look like? The positive half wave.
Same.
No. Okay.
Doesn't have like multiple pumps.
You're thinking of you're getting really close to a full wave rectifier. Okay, so what do capacitors not like doing? Yeah, they don't like changing voltage. what are they really good at doing?
Changing current.
Yeah, yeah, like they can change current instantaneously, basically. But they don't like changing voltage. And we're currently measuring voltage across that capacitor. Let's say it's like a medium-sized capacitor for the application. What does that imply for our waveform if it doesn't like changing voltage very much?
It's gonna be less of a wave.
Yep. Yeah. So if this is, I'm just gonna call this 1 volt because it's easy. 1 volt. I'm gonna draw something similar here. We're gonna hit the same peak. But assuming that this has been running for a while, we're gonna be hitting it and coming up steeply. We're gonna match this same curve here. Sorry, my art skills are showing. Okay, there. So that's the first half of the half of that wave. Can anyone tell me what it looks like from here to the green line?
Linear, but new.
Yep. There. All right, and now what does the next negative half wave look like? I'll do a more thorough explanation of this in a second. I'm just like same maybe yours turn. Yep, exactly. Yeah, it's just gonna keep going. Oh God. There we go. And now, assuming we have another positive half wave here, it's gonna hit that wave and it's gonna pop back up like that. Yeah, so why is that the case, right? There's 2 stages, positive half wave, negative half wave. If I erase this and erase this, if you're on your positive half wave, so that first thing we're analyzing just now, you have current flowing out of your voltage source, through your diode, through your resistor, and then back up here, right? But you also have current flowing into your resistor, or sorry, into your capacitor and charging it. Because capacitors can take up so much current so quickly, it basically just hits that part of the sine wave and it goes whoop and hits your maximum voltage. Also, at the same time as it's charging your capacitor, it's also feeding your load. Then, once you're moving on to your negative half wave, wait. Yep. Your capacitor feeds your load. So you might notice that you're like only really charging for like a very brief period of time here, and then you're discharging for a really long time. So you kind of need a large capacitor for this because of how long you're discharging versus how long you're charging for. And then like the voltage from here to here, let's just call it V ripple. Yeah, that's important. You'll come across that on your project one. It's like one of the key specs that they make you like report. Yeah. The reason why I draw it like this is because this is kind of like, you can set up your LT spice to kind of look like this, and then it makes it really easy to track like your source to your output. And then you can be like, okay, this is what my output looks like this. Yeah. And not only is this useful for your project, it's also useful for your exam.
What is VO2, the first negative sine wave?
Oh yeah, sorry. VO2 is with the capacitor. VO is without the capacitor.
Or I was meaning like what is it like in this?
Oh yeah. It's harder to draw like that. Like that. Yeah, because this region and this region are the same.
So because it's discharging, does it have to, so these bubbles, does it have to become larger, like, as it goes on, because I don't know if it's just the way that it's shown, but it looks like it doesn't stay level, does it? Like, it's not growing the same, I don't know if that makes sense.
I understand.
Or is it like growing each time?
I understand what you're saying. That's just because I can't draw straight lines.
Okay, no, that's fine.
Yeah. Sorry
I
about
just
that.
didn't know if it was like during the discharge, does it end up like where it was previously?
Yep.
Oh, okay,
Yeah.
thank you.
Yeah, so when you're starting the device, you'll have like some amount of charging period, a certain amount of milliseconds. And then once you've charged it, it'll enter a steady state and then
Gotcha.
remain exactly the same.
Is there a name for that region for when the charging actually starts, that lag between?
I don't think so.
Not relevant?
Not relevant, yeah. I thought I saw it, and it's no, okay. Cool. Yeah, that's all for that one. Any other questions? I can still see like a little bit of confusion.
If we see something similar on the test, should we just always assume it's been active for a very long time?
You assume steady state. Yeah. The value of your capacitor, the value of your resistor, and then the specific diode you have will drastically change your startup like waveform and like voltage and stuff. So yeah.
So for the first VNOT, the second section where it's the sinusoid, is that just because the current is going the way it's supposed to go and it's stopping the voltage of the actual source?
Yep.
Okay.
Yeah. No capacitor means you just have a resistor and a diode. So as soon as the diode is happy to start conducting, then you'll see the same waveform. Just off the load now.
And then it's 0 for the other ones because it's negative, so it's going the other way.
Yep.
Which means it can't go up that way.
Yeah. Okay. I just thought of another thing I could add on here. So if we have 1 volt peak, oh, I forgot I wrote this. Ignore that. Let's just say this is X. What is X if you have 1 volt peak on the top of your sinusoid?
1.
So you said 1, you said 2, and you said 1.5? Oh, 0.5. Was it? No, because we're just looking at only the peak value. So if this is 1 volt and this is X and this is 0 volts, the delta between 1 volt and X is the voltage drop across the diode while it's being forward biased. 0.7? So yeah, I heard it. Yeah, so the typical voltage drop that you see for diodes is 0.7 volts. Sometimes it's not that. Most of the time it's not that. But under select test scenarios for certain diodes, it'll be that. And in the case of when you're making assumptions of for voltage drops for diodes, you always just assume 0.7.
On the exam, will he like specify, or you, I don't know who's writing, if it's ideal, or do you just always assume if it's in a problem like this, it's 0.7?
If it matters, it'll be specified, or sorry, if you're assuming it's ideal, then it will be specified as ideal.
Otherwise, assume there is.
There is a voltage drop, yeah. Cool. Any questions before I go and erase this?
What does that make X then? Final answer.
You know.
Okay. Oh,
1.7.
Was that?
1.7.
Yeah, 1.7. Because you have 1 volt here, you got minus plus 0.7 here, and then you got 1.7 there.
so don't look off of the amplitude, or don't look at the amplitude.
Well, it is technically the amplitude.
So that one would reflect, your graph would reflect.
Yeah, my graph would be it would be your amplitude minus the voltage drop of your
Oh,
diode.
it is that.
Yeah.
Oh, so like before when it was 10, it would be a max of 9.3. Like I think if we had to graph it.
Yeah.
In my label.
I chose 1 because I forgot I put 10 here. That's my bad. Okay, cool. Anyone else want to like write this down before I erase it? Okay, cool. Uh, you guys know what this one too? Yeah, sorry for writing so far over on that side. I know like for everyone over here, it's really hard to see. Cool. Okay, so I think this is the second to last one. So very similar. And I'll not make you guys suffer as much this time. Okay. Yeah, let's just go through the same exercise again, but I'm gonna do it backwards this time. I'm gonna draw the current flow, and then once I'm done drawing the current flow, then we can draw the graphs. So we're gonna start with positive half cycle, and then once we're done with positive half cycle, we're gonna draw a negative half cycle. So positive half cycle, we got the current flow in this direction. It's gonna flow through this diode. It's gonna flow through this resistor. It's gonna flow through this diode, and then it's gonna come back through here and make everybody happy because your devices are powered. What does negative half cycle look like? Let's call this 1.1 plus 0.2 plus 0.3 plus 0.4. So where's current flow? From which point to which point first? Yep, starts at 1. Yep, goes to 2. Yep, then it goes to 3.
Four.
Yep, then it goes to number 4. So if I were to draw that out, go up, through, up, and then back. Okay, so now we know X, it's 10. What is the voltage? VO across R during the positive half cycle, during the blue half cycle. Yes. Yep. VO equals 8.6 volts. Positive 8.6 volts. Why?
Because you got two diodes, which both have the drop 0.7.
Yep. Yeah, exactly. Okay, so now for the other half cycle, what is VO? So current is flowing on the negative half cycle through the same direction. Yep. So you would have VO equals, again, positive 8.6 volts. Note that this is peak. This isn't RMS. This isn't minimum. This is just at the max of that sinusoid. Okay, so now that we got that, let's go ahead and draw those graphs again. Starting with the positive half cycle, negative half cycle, terminating there. And then okay. This is volts. This is VO, and this is time. V source. And I did it again. I put it in my corner. I meant to put it over there. Sorry. Okay. So what does it look like during the positive half cycle here? Yep. Yep. Okay. What does it look like during the negative half cycle? Yep, still positive. Whoop. And I have a couple of mountains. And yeah, that's kind of the magic of the full wave, right? Is now you have 2 pulses instead of 1 pulse per full cycle. Granted, you have 4 times as many diodes, but diodes are cheap. Energy isn't. So depending on your application, depending on how big of a capacitor you would need, this can make economic sense.
Can you explain for VO why it's 8.6 and it wouldn't be like 9.3? Since like on the path there, it only goes through the 1 diode before it gets the P2.
Yeah, good question. So this is grounded. Well, not actually, it's a sinusoid, but you have your current coming through here in your first half cycle, right? The blue one. Negative, positive 0.7 volts. And then you have your voltage across here. And then you also have to dissipate negative, positive 0.7 volts across this diode before you get to your ground. So that's something to note. Your load isn't grounded. At least not in terms of how your source sees it. Your load is kind of floating between these two diodes, and so when you pass current through both of the diodes, only 8.6 volts ends up across your load.
So if like one end of the resistor was connected directly to ground, then it would only be the one diode, but since it's in between the two, and the second one's kind of before ground, that's why it's twice.
Yep.
Okay.
Yeah. But keep in mind, like in a sinusoidal circuit, the concept of ground is kind of misleading because like I could stick a ground at P2 and like at least in terms of this source and this load, if I don't say what ground is connected to out here in the ether, then like no current's going to pass through it, right? So yeah, I could stick it over here. I could stick it up here. It doesn't really matter. In your LT Spice software, it would, because it would change how your graphs look. But in terms of like an analytical test where you're asking these kind of questions, like how much is across your load, how much is across your diodes, how much current is flowing in this specific circuit, it doesn't really matter.
Okay.
Cool. Yeah, everyone done with this? Can I erase it? Sweet. Actually, I don't even think I need to. I think I can do it over here. Okay. So you know how I said that 0.7 volts is kind of like a misnomer? Like it works as a really good like approximation for like a lot of stuff. But technically almost no diodes are going to operate exactly at 0.7 volts all of the time. That's due to kind of two things. Number one is manufacturing. Three things. Number two is temperature. And number three is let's just call it like chemical properties. So like the specifications of the diode. Specifications. Manufacturing, meaning like if you have 1,000 diodes and you were to plot like their VF, and you'd probably see a bell curve around your desired VF. And if your specification of your diode is 0.7 volts, then some number are going to exist at more than 0.7 and some are going to exist at less than 0.7. You don't need to know this, but yeah, it's useful information for if you're doing a senior design project or working in industry or whatever. Number two, temperature. Your book cares a lot about this. Equation 4.1, or sorry, 4.10 is a very nice equation. It's ID equals IS e to the power of VD divided by VT. I really briefly asked a question or mentioned thermal voltage, VT, and I think one of you guys asked me a question about it after the lecture. We just always assume that it's 0.025, 0.025 millivolts. Unless otherwise stated. It's kind of like how we assume that voltage drop across a diode is always 0.7 volts. You always assume the thermal voltage is 0.025. And you know how I was saying like in a lattice at a certain temperature, you're gonna have some amount of electrons like jump out of their locations, their covalence bonds. That is basically what this is saying. At a certain temperature, you're gonna have like a certain amount of bonds broken, and that manifests as a charge. That is the charge, if I read this correctly. And we just assume it's this voltage. VD is your voltage drop. Unless specified, you just assume it's 0.7, right? IS is a constant. I did not read enough to know exactly what that means, but it's a constant. You just assume for your particular diode, if it holds for one set of conditions, it holds for another set of conditions. And then ID is the drain current. Yeah. So let me draw a circuit. Yeah, that's good. Also, I know this has been going for a really long time. You guys must be like so tired. I'm tired. Yeah. Okay, so let's say that you have like an ID of 10 milliamps. And then let's say your data sheet says that at 10 milliamps, you're going to have a certain amount of voltage drop. You're going to have 0.7 volts as your voltage drop. So you don't know your IS yet, but you're given your VD. And because thermal voltage is basically always just assumed to be 0.025, we can say that. And now we have an equation we can solve for IS, and that would be good because as we change our current, our voltage drop across our diode is also going to change, but IS will remain the same. So let's say we have 30 milliamps. How would you solve for VB? Yep. Do you guys hear that? You plug in IS to figure out VD. Yep, that's everything for that. sure there's some other like good equations that you could know for chapter 4. Um, but in terms of like what I'm actually prepared to tell you guys, I feel like that's basically it. We could do one more op-amp problem that's actually kind of nifty if you want. Yeah? Okay. Cool. Okay, so go positive. Negative. I R. Let's say your VN equals 1 volt, or let's do 10 volts. And your R equals 10 kilo ohms. And we're looking to solve for IO instead of solving for a VO. And then this is a resistor or a inductor or a capacitor or whatever that creates some amount of impedance. What would be your first step to solving this?
You say that IO is also going down through the 10K?
Yes. Okay. What's next?
Is there a ground anywhere or no?
No, yeah. I could draw one if you want. It doesn't actually change the circuit though.
This is the voltage drop across the R, the same as VN. No.
Yes, but how did you come to that conclusion?
Because the top op amp, the positive and negative terminal share the same, so it's basically just plus. The positive terminal, and then the same with the bottom, so then it's just like a would be negative, yeah. And so then it's the same node, so then it's the same across R.
Yep, exactly. So with that in mind and this in mind, what is IO? One milliamp? Yeah, because you got, was it 10 volts divided by 10 kilo ohms? Yep, 1 million. So can anyone tell me like the significance of this circuit? Like why is something like this useful?
The current supply.
Yeah, exactly. So you can supply a voltage here and here, and you don't have to worry about whatever it is that's sending your voltage having current be pulled through it, right? Because there's no current getting through here, there's no current getting through here, but your voltage is ending up here, and you can bias that amount of current by changing your R. Then whatever amount of voltage, or sorry, whatever amount of current you send through your R gets induced across your ZO. So with this circuit, you can change voltage into current without pulling any current from your voltage supply. And there's another example of this in your book. It's more complicated to analyze though. So this one is like pretty sweet. Again, not directly applicable to your exam, but the method that you just used in order to solve for it is.
Or can you explain how? I would say like how you found what like that you found. But what like nodes did you? Cause I understand, yeah. What like nodes did you use? And then because it's obviously going across the resistor, right? Because you're using 10 kilo ohms.
Uh-huh.
So then did you just do it from the top node to? Okay, gotcha.
Yeah. So I just took the 10 volts from up here, translated that over to V1, and then I took the 0 volts at this node here, and I translated that over to V2. And V1 is the same as here, and V2 is the same as here.
Right.
And so I can just solve directly for IO, which I know can't go into this, and I know it can't go into this.
Mhm.
So it has to come from here and then through here into the other output.
Gotcha.
Yeah.
Okay. And that bottom node is 0 volts.
Yeah, sorry, I wrote ground, but it's
Okay.
it's 0 volts.
Okay. Thank you.
Yep. Cool. That's everything I have written down. I'm surprised we got through it as quickly as we did. You guys did great. Yeah. Go for it.
So what did you say you know, the importance of this was? You saying you changed voltage to induce some, or what was the wording you used?
Yeah. So you can change R. If you know what your VN is going to be, you can change R in order to induce a current into ZO.
Okay.
Yeah.
Why did ZO not
ZO only doesn't matter because of how we analyze the current. So if ZO was very small, this op amp would not have to produce very much voltage on the output here. So your relative voltage, so let's call this V out, for a small VO would be small. But if you had a really large ZO, then your V out would be huge. So from a circuit analysis perspective, when you're designing this thing, it would matter. But in terms of analyzing how much current gets through it, it doesn't. Did that answer your question? That was kind of roundabout.
Yeah.
Okay. It's more of a brain teaser than a direct applicable. Yeah. Unless for your senior design project, you have to make one. Okay, yeah, that's everything I have. Thank you guys for coming.
How useful will like the what problems that will sign? How useful will like some of the later problems.
Oh, hard?
Yeah.
You mean like chapter 4?
Oh, I guess for chapter. So I feel like later like last third.
We didn't get to the.
That's right. Like one of them is.
Okay. But like when you said for chapter 3, the only thing that stuff that he assigned, what do you mean by that? What was it chapter 4 you said?
Chapter 3, because that's the ones that that's the ones that he's gonna make me do.
Oh, okay. So you're just like, don't worry.
I'm gonna try to avoid using because it's pretty late to just drop on people like, hey, you're gonna have to do like numerical analysis for like these problems when I announced on Wednesday, like they're not gonna be anything other than what's on the slides. So I'm trying to make it as similar to what as many people have seen as possible.
Okay.
In classes. I don't even know.
Oh, like while he's.
Just writing down what he's writing down.
So, that's take the time later to process it, like.
Just he gets speeding up.
I like the.
Yeah.
Does he finish his lectures early?
Actually, put it on.
He just votes.
Draw he's doing.
Yeah.
He doesn't know what he's doing?
No, I don't have any sort of thing about what
Oh,
he's doing, yeah,
right.
he just says it, and he definitely knows what he's doing.
Yeah, he's really.
Great, yeah, but.
Yeah.
Yeah, no.
Or I appreciate you, bro.
Yeah.
Thanks so much.
Nice to meet you.
Clutch, thank you.
Of course, thank you.
Best of luck.
What slides were you referring to?
They should be on Canvas. It's a lecture 3 TA annotated, so like underneath my annotated slides.
Then our modules, I don't know. Oh, wow,
And then,
annotated,
yeah. And then lecture.
Okay.
Yeah.
Okay, T said this is gonna be like a really good idea of stuff we'll see.
Yeah, so I was trying to pull all of the questions from these slides, but he said they're too easy. So then you're gonna get, these plus some more difficult ones.
Okay, cool, thank you.
Yep. Yeah, expect numeric for the more difficult ones,
Okay.
from the book.
I just have two more quick questions. So
Yeah.
like for the op amps, for the ideal ones, is it mainly just that you need to know the voltages or the terminals are the same and there's no current? Or I forgot for ideal op amps, wasn't there also something about like the gain? Or is it mainly just those two things that are important?
So the way I was teaching op amps, you don't pay attention to the gain
Okay.
necessarily, unless you're calculating for it.
Yeah.
And then, sorry, what was the other question you had?
The other one was like related to, I didn't ask it yet, but it was like
Oh.
diodes. How do you tell like which side is gonna be the positive and negative when you're like for the one problem where it's 8.6? How do you know like when you're supposed to add and like subtract? Cause like the plus and minus were different depending on the diode.
Oh,
Like,
probably.
is it always like the end where like it's the triangle and then the line isn't like the line end is always negative or positive or like, cause I know resistor or with current, it's like, it goes from positive to negative. And so is that just like how it applies to that? You just follow the current?
Kind of. So if you have a voltage source here,
Yeah.
let's say it's plus minus like this,
Yeah.
you're gonna have to go and then copy this notation across the diode, right?
Okay.
So it's gonna be plus minus.
Yeah.
But let's say this is a sinusoid, and then you flip from the positive half cycle to the negative half cycle, you're gonna have positive, negative
Yeah.
now. So you're gonna have to redraw these and be like, okay, now it's,
Okay. So it
This
depends
way.
on the source that it's pulling from.
yes.
And so this would be like forward bias since it's like,
Mhm.
and then the other way would be reverse bias.
Yep.
No current. Okay, got it. Perfect. Thank you so much.
Yeah, you're-
Appreciate your time. Have a nice rest of your weekend.
Yeah, you too. Best of luck.
Thanks.